All right, I wanted to help you visualize a little better the stuff we learned today, which was points of concurrency with triangles. So circumcenter, incenter, centroid, and orthocenter. So remember, the circumcenter comes from constructing the perpendicular bisectors. So here are the perpendicular bisectors of the three sides. And remember, if you're on a perpendicular bisector, you're equidistant from the endpoints. So for example, the circumcenter is where these three meet. So the circumcenter is on this perpendicular bisector. So it is equidistant from A and from D. But it's also on this perpendicular bisector, so it's equidistant from A and from C. So it's actually equidistant from all three of these sides. And that's the circumcenter theorem. It says that the circumcenter is equidistant from all three, vertices, not sides, all three vertices of the triangle. We can also create a circle here where the circumcenter is the center and this distance is the radius. And notice, even if I move the point of the triangle, that circle will always perfectly hit all 3 points. For an acute triangle like it is, the circumcenter is inside the triangle. For a right triangle, like this, notice the circumcenter is like on the hypotenuse. And for an obtuse triangle, it ends up being outside the triangle. But the circle always is possible. Okay, the next one is incenter, and that comes from angle bisectors. So if I do the angle bisectors here, right, so this is the angle bisector of angle A, angle C, and angle D. They are concurrent, which means two or more lines that intersect at a single point. That is the incenter. And the incenter, remember, because it's on an angle bisector, it's the same distance from all 3 sides of the triangle. Because remember, if you're on an angle bisector, your perpendicular distance is the same to the 2 sides of the angle. So these perpendicular distances, let me hide these perpendicular distances are the same length. And that is true no matter where the triangle looks, or how the triangle looks. Okay? We can also make a circle using the incenter as the center and this distance as the radius. That makes this circle, which perfectly just touches at those 3 points. And again, if I move the triangle, that incenter circle, which is called the incircle, will always just touch the 3 sides of the triangle perfectly like this. The incenter will always be inside the triangle because the angle bisectors will always hit inside the triangle. Okay, the third one, probably the most important one, is the centroid. The centroid comes from the medians. And the medians, remember, a median goes from a vertex to the opposite side's midpoint. So these are 3 medians. So this is a median, and so is this. Where they intersect is called the centroid. The centroid divides each median in a 2-to-1 ratio. So the centroid to B is twice as long as the centroid to M3. And that's true on all 3 medians. The other way to think of it is the centroid to M3, that distance, is 1/3 of the entire length of the median. And B to the centroid is 2/3 of the entire length of the median. And here are some measurements to look at. So we can focus on this. From B to the centroid, divided by the centroid to M3 is 2, so a 2-to-1 ratio. And these two also show that 1/3 to 2/3 ratio as well. So B to the centroid divided by B to M3 gives me 0.67, which is 2/3. And centroid to M3 divided by B to M3 is 1/3. Please note the distance from the vertex to the centroid is always the longer one compared to the centroid to the midpoint. Okay? And again, notice if I move the triangle around, the numbers over here change, but the ratios never change. So those ratios, which are the centroid theorem, never change. So that's the centroid. Okay, and finally, we have the orthocenter, which comes from the altitudes. And an altitude, remember, goes from a vertex perpendicular to the opposite side. It doesn't bisect anything necessarily. By definition, it is perpendicular to the opposite side. So this is an altitude line, this is an altitude line, and this is an altitude line. And they intersect at a point called the orthocenter. And the orthocenter can be inside the triangle like this. If I have a right triangle, the orthocenter ends up being right at the right angle. And if I have an obtuse triangle, it ends up being outside. Remember, the yellow is the original triangle, so it's outside the triangle in that situation. Something that's useful with altitudes is we typically use altitude, well, we have to use altitudes, the segment here, as the height of the triangle. So if I choose this as my base, then the distance from here to here, which is the altitude segment, is the height of the triangle when I'm calculating area. One other final thing that's a little interesting is the orthocenter, the centroid, and the circumcenter are always collinear. Just an interesting fact. So if I move this triangle out, notice these points are always on the same line. And in fact, all 4 points, the circumcenter, the incenter, the centroid, and the orthocenter, would all be the exact same point if I have an equilateral triangle. Let's see if I can make that happen for you. Yeah, there, something like that, right? They would be exactly at the same point.